Ta-da! Introducing the latest kitchen trend, the periodic table and the kitchen sink, of course. In this micro video, we're going to learn about the periodic table and in particular, the atomic radius trend. Let's get to it.
Hello, everyone. Today, we're going to discuss the periodic trend, the atomic radius. To do that, we're going to first explore the background information required to understand this topic. Then we're going to discuss how atomic radius impacts how elements react with one another. And then finally, we're going to discuss how this is possible. So let's get to it. Two major background pieces of information that you need to know for this topic are Bohr-Rutherford diagrams, how to draw them and how to interpret them, as well as the electronic structure of atoms. What's inside the nucleus, including protons and neutrons, and how that makes the nucleus positively charged, and the surrounding electrons, which make the atom negatively charged. Together, that accounts for the attraction, which we will see when we discuss our atomic radius trend. If you are unsure about these two concepts right now, I suggest to review them before moving on. Now let's take a look at what happens when you potentially react to really reactive metals and non-metals.
Tube here containing cesium. Cesium is found in the far corner here, and it is the most reactive metal, the entire periodic table, even more reactive than francium. This is a radioactive element and it decays, but actually cesium is more reactive than this. It's the most reactive thing we can find. Now, why have I come up to Leicester? I brought this because I want to see how it reacts with the most reactive non-metal in the entire periodic table, and that's the element fluorine.
So why are these elements so reactive?
Now, to answer that previous question, we must first define what a periodic trend is. The definition of a periodic trend, let's start with periodic. Periodic refers to the pertaining to the periodic table, whereas trend refers to specific patterns that you observe, usually it's based on something else. So putting it all together, we have periodic trends, which means specific patterns that you observe in the periodic table due to the properties of the chemical elements. Now recall, we have multiple periodic trends in the periodic table. Today we're going to deal with one of them, and that is the atomic radius. Let's define atomic radius. Atomic means pertaining to atoms, and radius is a distance from the center of the circle to any point on its circumference. Putting it together, atomic radius is the distance from the nucleus to the outermost shell in an atom. The units given are 10 to the negative 12 meters, or 1 picometer. This is incredibly small, as we cannot see atoms in real life. Here we have our picture of our atom. This is sodium. It is going to be, the atomic radius is going to be from the center of the atom all the way to its point on its circumference. If I had drawn this correctly and symmetrical, any point would have been the same distance all the way across. So why is cesium, right over here, so special? We can ask ourselves, what is the trend from hydrogen, H, to cesium over here? Now note, we typically ignore francium because it's very radioactive. It doesn't like to stay in lab. If it doesn't stay in lab, it doesn't stay in real life at all. So it's really hard to isolate, and thus we usually go to cesium. But what's the trend? Does it get bigger, atomic radius, as we go from H to CS? Does it get smaller?
Now what happens if we go down a group? If we go down a group, we're adding shells to the atom each time. Starting off with lithium, we're adding one more shell to get to sodium, and then further, one more shell to get to potassium in the fourth row over there. So as we go down, we're adding shells each time, which is why it gets bigger.
All right, now let's investigate atomic radius as we go across the periodic table. How will this compare to going down the periodic table?
Now I'm going to model the second row of the periodic table using Bohr-Rutherford diagrams. Note we start with lithium and we're going to go all the way across to fluorine. Because we're on the second row of the periodic table, we're going to add electrons to the second row, to the second shell of the atom over here. Let's see what it looks like. I also encourage you to have the periodic table out with you while we're trying these questions with me. Now in our atom, we're going to have the nucleus in the center and one ring to represent the second row in the periodic table. I'm going to first model lithium, and we're going to see how that looks like as we go across the periodic table. In our lithium atom, we have 3 protons in the center of the nucleus. Recall protons are positively charged, and we have 3 electrons on the outer ring, which represent negatively charged particles. Recall also, protons are much, much bigger than electrons over there. In our lithium atom, we have 3 protons and 3 neutrons, and it's going to be around 152 nanometers in length, from the center all the way to the outside, like the atomic radius. Now, what happens if I add more protons and more electrons like I do with beryllium? Let's see. Now, with beryllium, I have only 113 nanometers. Compare that to the lithium ion, which had 152 nanometers. Nanometers is the unit that we use to measure a radius of an atom because it's so small, and it's 10 to the negative 9 meters. Very, very tiny. From here, we have 4 electrons in the outermost shell, and then we have 1 more proton that goes in the center over here. Because there's more protons and more electrons right now, they wouldn't stay in the same area. These electrons will now be pulled closer to the center because opposite charges will attract each other. It gets more obvious when we go to nitrogen, which has a 70 nanometer length. In a 70 nanometer length, we're going to have 7 protons and 7 electrons on the outside. Our atom is going to be much smaller at 70 nanometers, and it wouldn't look like this. It will look something like this, where we have 7 protons still in the center, but we also have 7 electrons on the outside, where our atom is much smaller now. This is because as we add more electrons and more protons, the attraction between these two gets stronger, and thus the outer ring is pulled towards the middle nucleus, making the atomic radius decrease.
To summarize, the trend for atomic radius as we go down a group, we're going to increase in size because we're adding new shells each time. Versus if we're going across a period like this, we are actually getting smaller because we're adding electrons to the same shell. Right? Again, we're not considering francium over here or neon because it's a noble gas and this is too radioactive. So why does being the smallest and largest elements, pretty much fluorine and cesium, allow them to be so reactive?
Well, being so different in size means one can easily transfer their electrons from one element to the other. That makes it easier for them to react because the transfer of electrons is what dictates our reactivity. So let's revisit that video and see what happens between cesium and fluorine, the smallest and the largest elements in the periodic table.
Action there between cesium and fluorine, this intense light, and I don't think many people have seen that before.